All right, good afternoon, everyone. Today we are I would love to get through all of these electronic structure slides. This is probably it's part of 3.3 and 3.4. It's the same presentation for both. But I guess this is more heavily 3.4, and then I have a worksheet to work on for 3.4. So if I can get through all of it today, that'd be wonderful. It just depends on what we need to take our time doing. But that would be my goal for today. And that way, when we come in on Wednesday, we can start 3.5. Just a heads up, your 3.4 homework is open. I would absolutely love everyone to get as much of homework as they can done now. Your quiz for 3.1 through 3.3 is open. Definitely recommend reviewing before you start that, because 3.1 through 3.3 it's unique, it's different. So if you haven't studied it, it's not something that you can just do really well on without preparing. But those are all open. We do have an exam. So next week, we're going to do more lectures. And then the following week, that Monday, we're going to have an exam. So let's just kind of think now, okay, let's prepare for that exam. What can we do? Unfortunately, I feel like a lot of the stuff we're doing in these next several classes are brand new subjects. And if you didn't have, it might have been a while since you've taken this in high school, so it literally is brand new. So just give yourself patience, and then of course give me patience, because this is a unique way of teaching, and I just want to make sure I'm doing a good job. So let's move on to electronic structure. The objectives for this 3.3 and 3.4 is to differentiate quantum mechanics from classical mechanics. So this is more of like a physics type of subject. We're going to describe the shapes of these orbitals. You'll see kind of images of what I mean by that, but we can kind of associate where electrons are based in specific orbitals, whether it be s, p, d, and f. The number of orbitals in a subshell and the number of electrons in a subshell. And I'm going to show you all how to shorthand. So even though it might be complicated to do it the hard way, there's always an easier method, and I'm going to show you both methods. We're going to use a periodic table of elements to construct the energy order of subshell, starting with 1s and the lowest, and move our way up. We're going to use the, I can't pronounce this, Aufbau principle, the Pauli exclusion principle, and Hund's rule to place electrons into an orbital energy level diagram. It's not so bad. It just takes a little bit of practice, but I understand it's like brand new at first. We're going to write the full electron configuration for atoms and ions. We're going to write the easier noble gas configuration, where it's a little bit more shorthand. We're going to identify valence electrons in an electron configuration. We're going to count valence electrons, and then we're going to classify as an atom paramagnetic or diamagnetic. So this is a lot we're including in these slides. So I'm going to do my best to keep it slow. Please ask questions. If you're confused, I promise you are not the only one. So make sure I'm doing a good job of making things very clearly. So this whole section is about electrons. Previously in the atomic structure section, we talked about looking at the periodic table of elements, finding an element and identifying how many protons, how many neutrons, and we can make an assumption, how many electrons. So usually the electrons, or kind of the number of electrons, if it's neutral, is the same number as protons, or the atomic number. But in this section, we're going to try to estimate where is the electron and talk about the electrons. So why does anyone care? It's a great question. Electrons can tell us a lot about what's going on, and when we're doing certain experimentation, like the electrons can really be important for why is this acting this way. So it may not matter to us as 1320 students, but for people who are high up in their sciences, it's very important. So electrons determine the chemistry of an atom. So going back to what we talked about with ions, positively and negatively charged particles, that's also based on electrons. Either they have extra electrons or less electrons. So those charges, it all dates back to how is the electron affecting it. So if I have oxygen O2 that's neutral in charge versus O2 minus, the identity of that is directly relevant to how many electrons are there. Question, if I have O neutral, oxygen neutral, how many electrons? So look at the periodic table of elements, find the atomic number. If it's neutral, it's the same. Grab a worksheet. Yeah, 8. If I have 2 extra electrons, remember they're negatively charged. What's the new charge? So it's 2 minus, how many electrons? So you have too many electrons now. 10. So if neutral is 8 electrons and I add 2 because of 2 minus charge, I know in our heads we're thinking, okay, take away 2. I completely get that. But it's the opposite. You have to add 2 to make it more negative. So it's more electrons. So it is all relevant, and yeah, it's going to test us. When we first learn about electrons, we all start with the Bohr model. I'm going to kind of like go quickly through it because the Bohr model is not the most accurate. It's just the start. So it's a Danish physicist named Niels Bohr from 1913. He looked at measurements of line spectra, planetary model of electrons and atoms, and he kind of made an estimation. So you might know what I'm talking about, and no worries if you don't. Where like he would say, okay, I have hydrogen here, and hydrogen is number 1, so it has 1 electron if it's neutral, and so that's how it looks. As you keep going across, there might be more and more subshells. So let's say I focus on maybe the next one, carbon. So if I go across hydrogen, helium, that means that those are 2 electrons, and then lithium, beryllium, boron, and carbon. So you, in high school, you might have done it this way where you add electrons as you're going across. That's the Bohr model. This is just the theory of why we started with the Bohr model. So the electrons, what he says was they orbit in a circle like planets around the sun. So it depends on the subshell. The lower the subshell, the less energy. The higher the subshell, the more energy. And it's just orbiting the nucleus like that. Unfortunately, it's not always that easy, but that was his original model, and that's how we kind of start learning about electrons. So this model fits experimental data like line spectra, but contrary to contemporary understanding of physics. So, yeah. The Bohr's model of the atom. Electrons orbit around the nucleus only in certain allowed stable circular orbits. So if I was to have something like hydrogen or helium, they would only orbit around this first subshell. We say subshells. And the lower the subshell, let's say I say this is the first subshell, n is the number for the subshell. N equals 2, n equals 3. So as I get further away from that nucleus, the energy of that subshell is getting greater. But depending on where those electrons are, it can only exist in this subshell. So sometimes, they might be over here, might here, but you have to fill the subshell before you move to the higher energy. So I think after the first 2, then it's like 8. I can even that out a little bit better. 4, 5, 6, 7, 8. So once you fill your subshell, you just keep going, depending on what element. But the maximum, the N2, N3, and further is 8. The farther away the orbit from the nucleus, the higher the energy. The closer the orbit is to the nucleus, the lower the energy. So that's why n equals 1, the lower subshells will be with less energy than the higher ones. Electrons can jump between orbits only by absorbing or emitting the exact amount of energy corresponding to the difference in energy in orbits. What I mean by that is, this is his theory, that if, let's say, I add light, I shine a nice light onto it, it might hit one of those electrons and bounce off, and it can absorb or emit the light, and that'll go to a higher subshell. So energy of the electron is quantized. That definition is electrons can't have any imaginable energy. It can only inhabit certain energy levels that are on a fixed distance from the nucleus. That's what I mean by, depending on what element, is it only an N1, only an N2? It's limited to that subshell unless I add light and excite it. So this is what I mean by absorption of light. So let's say I had an element outside and the sun hit it, or if I had it in a specific instrument where I can shine light onto it. The electron absorbs, so let's say this is an electron, this red dot. It absorbs energy from a photon. Remember, we talked about light, a wave. So a wave of light hits the electron. The electron absorbs the energy from the photon. So we found that the energy of an individual photon was like something like 10 to the minus 19 joules. Not a lot, but that is some energy. It jumps to a higher subshell. So it goes from, let's say, the N1 subshell in two subshell if it is excited like that. So it jumps to an orbit that is farther from the nucleus and thus at a higher energy. The object appears colored because it reflects all of the other colors. So if, let's say I have a red shirt on, you're seeing red, but it's absorbing red and reflecting all of the other colors. You see the reflected, not the absorbed light, or maybe I said that backwards. That's just the Bohr's theory. Emission of light. So this is what happens after the electron absorbs the energy. So previously, the light was hitting the electron. Now it's bouncing off. So absorption is when it hits it. Emission is when it comes off. So after it hits it, because originally it was here, let me do what it had on the last slide. You had the electron in the lowest state possible. The light hits it. So electrons, it'll then emit the light or the energy from the light, and it'll move to a higher subshell. So electrons are unstable in higher energy orbitals. It only happens for a very short time. It always will come back to the lower energy state. But this is just what happens when absorption is happening. But for that moment, it is in the higher state. So electrons give away some of their energy as a photon and are able to jump to a lower energy orbit. And then you see the colors when they're emitted. So just an example. If you take Gen Chem 2, you will do an experiment that deals with absorption. If you are taking 1135 with me, we also have a very similar experiment. So even though we're not doing this together in lab right now, you will see it at some point. It's not going to be testing you on this knowledge, but it's going to be a lot of fun just to, look at the color and measure the absorption. That's up until 1913. So we have developed better estimation of where the electron is. It's not perfect, but we have gotten better. So there's more experiments that happen, more data, more questions. So through the 1940s, the main parts of the quantum mechanical model took over, and we are still refining it. This is not perfect. So this is Heisenberg, Dirac, Schrodinger, Planck, Pauli, Hahn, and lots of other scientists develop these theories. All right, so let's compare the models. So Bohr was 1913, and then after 19, I'll do greater than 1913. So Bohr thought the electron was a particle, whereas in quantum theory, they're thinking the electron's acting more like a wave. And Bohr, he said that the subshells, like I gave examples like n equals 1, n equals 2, things like that. So depending on where they were in relation to the nucleus, where in quantum theory, it's either a shell or a subshell. Bohr thought that those electrons were orbiting the nucleus, where in quantum theory, there are orbitals around the nucleus. And I'll show you a picture of that. So around the nucleus, there's this cloud in certain directions, and we're estimating the electron is there. Bohr can say, okay, this is exactly where the electron is, but in reality, it's not possible. So we can describe with probabilities of where it's at, but it's not a perfect, this is where the electron is at every time, every moment. So unfortunately, in both models, we don't really know why. It's just something that we can't really explain. The electron is constantly moving. It's just how is it moving and where is it at? So we can estimate and refine where we think it's at, but we do not know exactly. Okay. So orbit versus orbitals. So in the Bohr model, like I showed you before, he was having those subshells based on the periodic table elements. And he can say, okay, well, the electron's here, and this subshell is here, it's here, and here, and it's going to rotate around the nucleus like planets around the sun. Doesn't happen that way, but that was his theory. In the quantum model, electrons behave like waves that then occupy different regions. So we might be able to estimate that a specific electron is in this part of the cloud, or maybe in this part of the cloud. So it's more of an estimation, and we're refining where do we think it's at. So it's a big idea in quantum mechanics as the Heisenberg uncertainty principle. So we cannot know both the position and the speed of a particle with an accuracy. That's the definition. So what I found out when I did more research and I opened this article was that we can figure out more about where the particle is at, but we lose all idea about the speed and vice versa. So if you can figure out closer and closer and closer how fast the electron's moving, we are less likely to know the position. So it's kind of like, that's the uncertainty principle there. On the next slide, I'm going to show you Schrodinger's equation. This is not something you will ever be tested in lower level chemistry. You won't really need to think about this until you hit physical chemistry, but it has a lot of relevancy because this is a very physics heavy section. And it's, you know, our forefathers, our scientists from before and how they discovered things. So I'm showing you the Schrodinger equation. It's really important, but it's not something I would ever, you know, give you on the exam and say, answer this. So don't be overwhelmed by it. We're not going to do anything crazy. It's just really important. So the Schrodinger equation is equivalent of Newton's laws of motion, of course, and Maxwell equations for very tiny systems like atoms. We can use Schrodinger equation to estimate the speed or the location of specific electrons. This is something you won't see until PChem 2 if you take PChem 2. If you're not, no worries. Up until now, we kind of, when we were finding an unknown, we only had one unknown. So like if I said solve for X, you didn't have X, Y, and Z in the problem. So it's much more straightforward for what we're used to is just solve for what's missing. Eigenvalue equations are a way where you have several different uncertainties and you can still solve for unknowns based on those several different unknowns. So like if I don't know my speed and I don't know my location, it would be an eigenvalue equation where I can still answer it with those two unknowns. Not something that we will be dealing with ever, but relevant to the topic. So the trade-off is that we end up with an infinite number of solutions because you have different unknowns. So for an atom, there are two variables with one equation. So we have psi, which is this. It helps us kind of give a 90% probability of finding where the electron is inside its orbital, and then E for the energy of the electron in that orbital, which we can relate to. Don't be overwhelmed by this. I just want to talk about it. But yeah, a lot of fun if you hit physics. The last time I saw this equation or had to use it was PChem 2. I wasn't enjoying it, but I know a lot of my friends really loved it. Up until now, like we've been talking about theory. After this kind of little section, we're going to start putting things into motion and how am I going to take what we're talking about right now and apply it to what you might be asked of on the exam. Okay, so yes, it's nice to know the theory, but this is just the workup of how we're getting to where we're at. So what do you do with an infinite number of solutions to an equation? Fortunately, we don't really need an infinite amount because we only have 118 elements. We're always focused on just elements. We need to be able to organize a system to keep track of the possibilities. So those shells, we kind of relate those shells to the rows. So if you look at the periodic table of elements, you have, row 1 is hydrogen and helium, row 2, lithium, all the way to neon, and so on and so forth. So with the Bohr model, we would say, okay, N1 is row 1, N2 row 2, and so on and so forth. The subshells are also important. So shells versus subshells. Subshells is based on the groups. So groups 1 and 2. When I say group, I mean column, but group is also column. So I'm going to say groups. Groups 1 and 2 would be the S subshell. If I skip over to boron through helium, all those groups, that is the P subshell. And then the transition metals are the D subshell. And then the last two ones, the lanthanides and the actinoids, those are the F subshell. So there's two things we have to think about with these problems. I'm not asking you to memorize it right now, but I'll show you how we can use it. So we're going to need to put a system into those orbitals. So we need both rows and we need subshells. So where is it in the periodic table of elements? All three of these are relevant. The Aufbau principle, we're going to build an electron configuration by adding electrons one at a time to the lowest energy orbital available. So we're going to use the periodic table of elements. If you have your copy of the periodic table of elements, you don't have to look over there. I'd ask you to get it out and have it ready. If you don't, no worries. If you're at home, I would probably have it up in a different tab on your computer. If you're in person, you have the periodic table of elements with you. So the Pauli exclusion principle is there's a maximum of 2 electrons in an orbital with paired spins. And then Hund's rule. put electrons and an energy level into orbitals singly first before pairing. And I will show you exactly what I mean by this. The more you practice, you have to think about these rules. It just comes naturally. So these electron configurations are highly repetitive because they always follow these patterns, which means is once you're comfortable with these patterns, it's going to be very simple to always be able to make a good electron configuration. The S subshell. So I pointed out its columns or groups 1 and 2. So these subshells are one orbital. So you might, say we have an S orbital here, and it has 2 electrons. So you'll start to see me draw an electron like that. So if it only has 1 electron, like hydrogen, it would look like this. So it'd be, what row is hydrogen on? 1. So this would be 1s. If I wanted to focus on helium, I know helium is all the way in the last row, but helium is one of those that it can't have more than 2. So it acts like a noble gas, but it's actually right next to hydrogen when it comes to these orbitals. So it's confusing, I know, but it's important to be able to know what helium is. Helium only has 2 electrons. So you'll start to see me kind of do it like that. So 1 electron will be up, 1 electron will be down. Let me move further. What if I wanted to focus on sodium? What row is sodium on? 3. So yes, you'll fill the rest of these orbitals in, but I just want to say like 3s, it would just have 1. So row, and then where does it belong? I'm going to give you a lot more practice, so I'm not trying to confuse. I'm just saying like this is where the S subshell is. It can only have a maximum of 2 electrons, and it's 1 orbital, 1 circular, very close to the nucleus. This is the nucleus right here. And the S is the lowest energy you can possibly be, and it's closest to the nucleus. The P subshells are going to be boron group all the way to helium, or neons group, I'll say underneath helium. So these are a little bit more different. They have these dumbbell appearances. So they can have a maximum of 6 electrons. So let's say I have row 2p. So if I look at carbon is on row 2, and it's in the P block. So it's P block. So I would say we have 2p, and then there's how many? Never mind. It'll be like 1, 2. We're going to get into this a lot more later, but this is how you would see the 2b block. Okay. So it could be right here, it could be right here, and it could be right here. I'm not going to test you on if you know which one it is. I'm just showing you what it might be. And since this is further away than the S block, you can see how it fills more space and it's further away. The D subshell, this belongs to transition metals, and it has a different shape. It's like more like a clover leaf shape. There's more options for those electrons to be because there's even more electrons there. So in the D block, because there's a lot more elements in the transition metal block, there are 10 across. So that means that there are 5 orbitals that can fit 2 electrons each, so a total of 10 electrons. And then the F block, which we really do not hit on for us. This is probably the most complicated, but it's like multiple clover leaves. And this one, if you look at the bottom 2 little rows that are lanthanides and actinoids, there are 14 across, which means there are 7 orbitals with 2 electrons each. Every orbital can fit 2. If I have 1 orbital, like an S block, it can fit 2. If I have 3 orbitals, like the P block, I can fit 6. So it's just 2 per orbital. This is going to be, if you have your worksheet out and ready, I'm not going to ask you to start working on it, but this is kind of could help you answer that first question. It says type, and like the type would be the S, P, D, or F. There's the shape. So the S is like a sphere. It's just a giant circle. The P block is dumbbell shaped. D would be cloverleaf, and then F would be double cloverleaf. So it's kind of like going over those previous slides if you want to answer that real quick. You know, grab one of those worksheets so I can take a look. So degeneracy, I'm not sure what that means just yet. Maybe we haven't hit on that. But the max number of electrons, that would be, okay, if I have 7 orbitals and each of those orbitals can fit 2 electrons, the max number of electrons are 4. So that's how you can answer that last row. I need to take a look at what degeneracy means yet. Okay. Here is how we can start simplifying it a bit. With the Bohr model, this is kind of like how the Bohr model was, where the closer the shell was to the nucleus, the lower the energy. So the first row would be closest to the nucleus, lowest energy, and if you go to the second row, it's slightly further away. Third row is slightly further away. Fourth row is slightly further away. So for the first row would be the lowest in energy, and then the furthest away will be the highest in energy. So on the right-hand side is using the quantum theory. So left is Bohr, right is the quantum. And if an electron has, sorry, what am I saying? If an orbital has 2 electrons, then each of these lines can fill 2 electrons. So I'm going to do some examples of this, but like if I had hydrogen will only have 1 electron. So I would start at the very lowest one and work my way up. So hydrogen with 1, helium with 2. What's after helium? Lithium, okay, so it's number 3. So if it's neutral, 1 additional electron. So beryllium, boron. So here's important. According to Hund's rule, we don't do it like this. You don't fill up 1 orbital at a time when you have multiple next to each other. You do 1 electron to fill it across, and then you fill in. So boron, and then watch what I do. Carbon, nitrogen, and then now I fill in the rest. Oxygen, chlorine, neon. So each of these electrons is being related to an element on the periodic table of elements. So if I was to give you an element, can you fill this in? So you start from the lowest and you work your way up. I'm going to go back to lithium real quick. If lithium is neutrally charged, but lithium, what charge, if lithium was an ion, what charge would it be based on what column and group it's in? Okay. If I had a +1 charge, would I have to add or remove an electron? So electrons are negatively charged. This lithium is positively charged. If I added an electron, it would now be a lithium with a -1 charge. Electrons have a negative charge. So
if you added 1 to a positive charge, does that not make it neutral? Why does that make it negative?
So, okay, an electron has a minus charge. Okay. If I add an electron to a neutral, I now have a -1.
You said lithium had a positive charge.
No, I'm trying to get it to a positive charge. Lithium, if I have lithium neutral, I'm just trying to show you how electrons will shape everything. So you can also play around by taking away electrons to show you the charge. So if I wanted lithium to be a positively 1 charge, I would have to remove an electron. So that would be lithium +1. If I wanted lithium with a minus charge, I have to add an electron. So just remember, electrons are negatively charged. And so if you need to figure out, okay, oxygen 2-, let's do oxygen. Oxygen, if it's neutral, how many electrons? 8. So I'm going to fill in until I hit 8. So 1, 2, 3, 4, 5, 6, 7, 8. That's oxygen. But we're most comfortably seeing oxygen as a 2-. If I want to get this to a 2 minus charge, I have to add 2 electrons. If I'm focused on oxygen. So you add electrons to get it to be more negative. You remove electrons to get it to be more positive. But let's go back to oxygen being just a neutral charge. Okay. Electron configurations are a way for us to take this and just write it out, because I'm not going to be able to take this picture and give it to you always. I'm just not. So if I was to take oxygen right here, I would write it like this, where you take your row, your value of N is your row. That first number is your row. The second number is the shell. So the subshell. So if it was the S, it could be P and whatnot. And then the last number is how many electrons are there. So oxygen, I will write down everything. So it'd be 1s, so oxygen. I'm just literally taking this and writing it down here because I can't always have this picture. So I'll take 1s and then how many electrons are in the 1s orbital. 2. Okay. Next, the next energy is going to be 2s. How many electrons are in the orbital? 2. All right, the next one is not as clear. 1, 2. Wait, it was option 3, 4. All right, so that will be 2p, and then what is the amount of electrons? 4. So a way for us to take this energy diagram and turn into what we call an electron configuration is you go from the picture with electrons just to writing it out like that. Okay. So once again, when you write it all out, you start with the row, subshell, and then amount of electrons. So just keep going if you go past this. So if I wanted to just say 1s2, by itself, that would represent helium. Helium is 1s2. If it said 1s1, that would be hydrogen. So a lot of other things we need to think about are valence electrons. I'm going to show you all how to count valence electrons much later on. We get towards the end of this. But valence electrons we can also count from using these electron configurations. So valence electrons are the outermost electrons. So if it was just hydrogen with 1 electron, that's just the valence electron. But as you get further on the periodic table of elements, let's say I'm looking at bromine, much further on, there's going to be if you look at bromine, if it was neutral, it's 35 electrons. That's a lot of electrons. But we're only focusing on the outermost electrons. So those are the only ones that can affect the properties of bromine. So I'll show you what I mean by that later. So they participate in chemical reactions. The lower ones don't, only the valence electrons. So all electrons in the highest number of shells. That is the definition of valence. So the outermost ones and the highest numbered shell or the row. There might be in more than one subshell, but that's going to be the furthest outermost electrons. Let's talk about magnetism real quick. There's some really nice videos. I watched all of these. I'm going to have us just watch this first one because we don't have time to watch all of them. But the definitions that are important, the one we're most comfortable knowing is ferromagnetism. That's the same thing as just I have a piece of metal and I have a magnet and the metal is strongly attached to that magnet. That's ferromagnetism. Iron is a really good one. It just means strongly attached. That's the ferro means iron, but it could be other metals. Some metals are just very, very attracted to magnets. For the definitions in this next section, we're going to be talking about paramagnetism or diamagnetism. So paramagnetism is more than one unpaired electron. So previously we had oxygen, where we had that 2p orbital, and the oxygen had 1, 2, 3, 4. Yeah, 4. Because there are 2 unpaired electrons, it would be paramagnetic. Paramagnetic means it's slightly attracted to a magnet. It may not be as attracted as ferromagnetic, but it is going to be more attracted to a magnet. And this video is going to show you what they mean by that. If it was diamagnetic, let's say I focused on neon. Neon would have a full p orbital because it has, two in the set, the S1, and then if you look at the p, it would be completely full because it has 6 electrons in the p. All electrons are paired. So you see that all of these electrons are paired, and these slightly repelled by magnets. Maybe I'll show you the last video too. That one's a really quick video. I can show you both. Maybe not. I don't think I got it up on time. Okay.
You might not think of water as being magnetic, but it is, and so are graphite, aluminum, and glass. This is a new and different category of magnet, called either para or diamagnetism, and it's different from the magnetism that you're used to. You're probably already familiar with ferromagnetism. Ferro means iron. An unmagnetized piece of iron becomes a magnet in the presence of a magnetic field. The effect is strong and lasts even after the magnet is removed. Paramagnetism is a similar effect, except that it's much weaker and temporary. Aluminum is a good example of a paramagnet. And so is oxygen, which is attracted to magnets. Here, I have a few milliliters of liquid oxygen, which sticks to the magnet. I'll explain why later. Gadolinium oxide and cupric sulfate are good examples of paramagnetic substances. Cupric sulfate is a salt that can be picked up by a magnet. Diamagnetic materials are exactly the opposite of paramagnetic. They are always repulsed. They would rather die than be in a magnetic field. An important example of a diamagnetic material is graphite. This specially made pyrolytic graphite is repelled by a magnetic field. Don't be confused. This is not static electricity or eddy currents. Graphite is repelled by a magnet, always, both by the north and south end. Pyrolytic graphite is a growing crystal of flat carbon layers, which maximizes the diamagnetic effect. Of course, the best diamagnets are superconductors, which at low temperatures provide exact opposite repulsion to whatever magnetic field is present when in chill. They are perfect diamagnets. The most famous and powerful diamagnetic is bismuth, element number 83 on the periodic table. The bismuth-powered boat sails toward the weaker magnetic field. One way to check whether an object is diamagnetic or paramagnetic is to see how it aligns itself in a magnetic field. Diamagnetic objects like glass will rotate to avoid magnets. Here, you see that the glass is diamagnetic. It twists to get to the weaker magnetic field. But aluminum rotates into the field, typical of a parallel paramagnet. On the periodic table, we see that aluminum has 3 valence electrons. So what does it take to understand what it means for something to be a paramagnet or a diamond? You have to know what the electrons are doing. Consider, for example, aluminum. We see from the periodic table that aluminum has 3 valence electrons. That's 2s and 1p.
Please focus on that row.
Now, it's that unpaired electron that makes it a paramagnet. This unpaired electron enables it to become magnetized. And it's that unpaired electron that's freely magnetized and attracted by a magnet. Well, what about a diamagnet, like water? Yes, the water molecule, it has all its electrons paired. It will not be magnetized. In fact, water is repelled by a magnetic field. The electrons come to lower energy as they are moved away from the magnet. In conclusion, when something is a paramagnet or a diamagnet, it tells you what its electrons are doing. In the case of a paramagnet, it has at least one unpaired electron. In the case of a diamagnet, it has mostly paired electrons.
I like these videos just because it helps visualize a lot better than what I'm showing you. So just seeing the metals and how they react. The last video is only like 40 seconds long, but if you have N2, if I had just nitrogen by itself, it would not be diamagnetic, but if you put two nitrogens together, it becomes diamagnetic. So if I take liquid nitrogen and put it on top of a metal, or sorry, a magnet, it just like flows right through it because it's repelled. So it's diamagnetic. But O2 is para. So if you were to throw liquid oxygen onto a magnet, it kind of like sticks. So if you have time to watch that last video, it's fun to see the difference between a paramagnetic oxygen and a diamagnetic nitrogen. But yeah, I'm gonna practice on the next slides, and we're gonna write electron configurations, and we are going to identify, is it paramagnetic or diamagnetic? So maybe, make a little cheat sheet in front of you. Para, unpaired, dia, paired. Right. I'm just gonna practice as we go through the periodic table of elements. Let's look at lithium again. If it's neutral in charge, how many total electrons does lithium have? So as I fill in this table, I should only have 3. 1, 2, they can only have 2 per. 3. So I'm done if it's lithium neutral charge. So if I need to write the electron configuration for lithium, it would be 1s2, and then what will be the next one? 2s1. As we increase electrons, we would keep going. If I wanted to like play around with the charge, that would also affect it. Like if I had lithium +1, it would remove that electron and you'd have just 1s2. If it was negatively charged, you'd add the electron, but let's just keep it neutral. So lithium 1s2, 2s1. What about, let's say, beryllium? Be, it's number 4. So if it was neutrally charged, it would have 4 electrons. And that would mean I'd add a second electron to the 2s. So that would be 1s2, 2s2. Now, is lithium para or diamagnetic? So lithium has unpaired electrons, so it would be paramagnetic. What about beryllium? Dia, because it's all paired. Let's keep going. Let's focus on, I already did oxygen. Let's do nitrogen. And I'm just doing nitrogen. I did not spell that one. Nitrogen. If it was neutral, how many electrons? 7. So 1, 2, 3. Okay. 4, 5, 6, 7. Just make sure you use Hund's rule and you do single electrons if you have more than one orbital. So N would be, let's write out the electron configuration. 1s2, 2s2, 2p3. Is nitrogen by itself, not N2, is nitrogen para or diamagnetic? Yes. Unpaired electron is para.
One when it's in, it's still para, like if there's, like let's say there's 2 more electrons,
Oh, yeah.
it would still be para.
Okay, so I lost my feed. If you're online, bear with me. It looks like I lost my feed. So if there were just one unpaired electron, it'd still be para. So the definition of para is one or more. So nitrogen has 3 unpaired electrons, it's still para. If it was fluorine with 1 unpaired electron, it's still para. I need to find, okay, so I'm back in.
And do the changes in charging obviously affect that too, right? So like if we were to change nitrogen to where they would all be paired, then it would be dia.
Yes, that charge would tell you. So let's say it was nitrogen 3 minus, which is the ion that we talk about the most. So charges affect it. If it's negatively charged, we add electrons. So let me change this 0 to a 3 minus. I would have to add 3 electrons. Shoot. Sorry, I'm sharing it on my computer, but it's not. Let me refresh. Bear with me. If y'all want to take a look at your worksheet while I figure this out, we're going to start our little mental break in a few minutes, but I need to get my computer able to run. Oh, the degeneracy, that's just number of orbitals. So for that first question, if it said for S, the degeneracy, you can maybe pick in line, it says orbitals. So there's 1 orbital, P would be 3. What would be D? Do you remember? 5, and then F. So yeah, that would be number of orbitals. I checked it while y'all were working. I'm gonna restart my computer. Number 2 is to say use the periodic table to draw it. So if you look on the left-hand side right here, it wants you to kind of do that little table I just had up there where it has like 1S, 2S, 2P. So that same table as before, like it wants you to do that here. I know it's very confusing. Okay, we're gonna take a mental break for the next 5 minutes. Hopefully my computer will be up and ready. I'll see y'all back in at 12:55.
When you're filling in this table, do you do? I don't know how to word this, like one number at a time? Like when you get up to, there's four S and then three B, just slightly above it, you fill in the three before you move to the four?
It's all about reading the rows. I'm gonna show y'all towards later in the slides, but if you're going across the row, it's the same thing. So 3D is at a higher energy than 4S because of transition metals. So I guess if you're following that, it's based on energy. So I would just count the electrons. So look at the periodic table of elements, count the electrons, and then just start and add as many electrons as you know that there's total. So let's say if I'm looking at nickel, just go until you hit 29 electrons.
Okay, but would you fill in four S first, or do you do all the three, then move to the four?
So based on the table that that we had up here, 4S is before 3D. So you fill in 4S before you touch 3D,
Okay.
based
So
on
you're
just
going
that,
basically from bottom.
from bottom to top. If you have that in front of you, you don't even have to remember where things are, you just need to know the number of electrons. But once I take that away from you, I'm gonna show you how you can still answer it.
Okay. Yeah, I just didn't know if you had to do all the three before you touch.
Nope, don't play around, yeah, just do lowest to highest. Mhm. And I know it's overwhelming, I struggle teaching this section, it gets easier. Sure. I promise you. It's like a puzzle, it may not make sense when I'm doing it, but I'm like, okay, it says it's always gonna be correct, right? It's an always, there is no, so it's like, as long as I can do the basics, yeah, I can do it.
In other news, Texas residents are going to be happy to hear this. It just came out, there's a new website where any Texas resident, as long as you live within
Is
the
that-
zip code in the state, you can apply to have your auto insurance rates reduced significantly. All you have to do to qualify.
Almost done. Thank you for your patience. Okay. Let's continue. I might not be able to erase this slide, but remember that if I add electrons, so if it's negatively charged, electrons have negative charge. So the more negative it is, the more added electrons you have. If it's more positive, you have to remove electrons. So nitrogen, if it was that ion that we discussed all the way in the ionic nomenclature section, 3 minus is nitrogen when it's an ion. So if I have a 3 minus, I have to add electrons. If it was something like, I don't know if I can erase. No, I can't. This would also be equivalent to neon. So neon, if it was neutral, would have 10 electrons. And if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, this would be the same electron configuration for neon. So 1s2, 2s2, 2p6. Is neon diamagnetic or paramagnetic? Dia. If all of the electrons are filled in, there's 2 in every orbital, it would be diamagnetic. Okay. If it was N3 minus, it would also be diamagnetic, but the reason why this one's para is because it has this 3 right here. Let's keep practicing. Let's move beyond nitrogen and let's move into the transition metals, because there's a great question about transition metals. Let's do iron. Fe, if it was neutrally charged, how many electrons? 26 electrons. You have to fill in lowest to highest. Don't get questioned about the numbers or the orbitals. Start from low and work your way up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. That was not pretty. I'll do another one. 26. So you just go low to high and fill it in with every electron. So the electron configuration is you start from low to high. I know it's going to get long, but that's okay. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then what would be the 3d? 6. Is it para or diamagnetic? Para. I would say majority of elements will be para because it's very rare for all of them to be filled. Very few have all of them filled. What about zinc? Let's do zinc. If zinc was a neutral charge, how many electrons? 30. So I need to add just 4 more electrons. So 1, 2, 3, 4. 2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, not 12. I don't know what I was thinking. 10. It should all add up to 30. All of these numbers and the exponents should add up to the total number of electrons. This should add up to the total number of electrons. It should all make sense. Is neutral zinc dia or paramagnetic? Every electron has a partner, therefore it's diamagnetic. All right, zinc. Does anyone remember the charge that zinc likes to have if it was an ion? It's one of a set number. It's zinc and cadmium are always +2. So I'm going to take this neutral out and I'm going to put a 2 plus here. If it's 2 plus, how many electrons? So if you have a positive charge, you're removing electrons. So a 2 plus means I am losing 2 electrons. So 30 minus 2 is 28. So I need to remove, 2 electrons, and that will also affect my electron configuration. Is zinc 2 plus diamagnetic or paramagnetic? Now it moves to being paramagnetic. So as long as you can count the electrons, you can always get these right. So if it's neutral, and I'm kind of emphasizing that because I have it on the quiz, and I have it on the worksheet we discussed last class. I think on my quiz, I'm gonna give you a little hint now because you're here now and you're talking to me. There's a question that says, assume everything's neutral, how many electrons? I'm not trying to trip you up. Whatever your number is on the periodic table, that's how many electrons in, because you're assuming everything is neutral. So you should get that number correct for everyone because I'm not trying to play tricks on you. I'm not trying to give you positive and negative charges, but maybe in the next quiz I will. But in this quiz, whatever number is on that periodic table of elements, if it's neutral, that is the number of electrons. That's why I'm really hinting at it right now. Let's go do arsenic. Y'all see arsenic, it's number 33. So I'll count 33. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18, 1, 22, 23, 26, 27, 28, 29, 30, 31, 32, 33. Yeah, that's arsenic. So it's very similar. We're just keep moving and chugging along. Okay. 2s, 6, 3s2, E6, 4s2, 3e10, 4e3. All right, it just keeps going. No matter what I throw at you, you just got to follow this trend and keep going up. I will also point out that 3D is lower in energy, higher in energy than 4s. I'll show you why in a little bit, but as long as you're following low to high, you will always get it right. Don't try to get yourself confused about the difference in these numbers here. Just follow this trend. Okay. And you might be asked to do electron configurations, double check the amount of electrons, is it neutral in charge, is it negative in charge? Arsenic is underneath nitrogen. Arsenic would prefer to be a -3 if it's an ion. And so then you have to go and just add those 3 electrons. So then it becomes diamagnetic. But if it's arsenic neutrally charged, it would just be with the 3 and be paramagnetic. So it's not so bad, but this is how you can kind of set everything up. It seems very confusing, but the more you do it, it's just following a pattern. You're making a puzzle, you're solving a puzzle. Any questions on that? Okay. That, as we get further on with more and higher up elements, I don't feel like writing this out. Like, that's a lot I have to write out. But there is a shorthand notation that I'm about to show you that can simplify and make your life a little easier. And that's called the noble gas configuration. So the way that works is, let's say I have arsenic right here. Look at the periodic tables and find the noble gas in the previous row. So arsenic is going to be in row 1, 2, 3, 4. So the noble gas, what is the noble gas in row 3? Argon. If I was to write a electron configuration from argon, it would stop here. This is argon because it has 18 electrons, and argon would look like this: 1s2, 2s2, 2p6, 3s2, 3p6. That's argon, right? So if I was to do the same process, I got argon done. It's diamagnetic, but that would be the same thing as this. If I want to shorthand it for arsenic, I can just, in parentheses or in brackets, I can put argon and then take whatever's left over. So everything after the last noble gas. So argon 3, 4s2, 3d10, 4p3. That is the shorthand noble gas configuration, is everything after the last noble gas. And so if I am comfortable with that, I can save myself a lot of time and effort not having to write it. Because what if I was asking you about bismuth? Like, no one wants to write that many in a configuration. But instead I can say, okay, xenon, and then do everything after a xenon. It saves you so much time and energy because I'm assuming you can do everything beforehand. But let's be real. It's easy to make mistakes the longer and longer and longer you go. So getting comfortable with the noble gas 4 configuration really helps. So the arrangement of electrons in a noble gas is very stable. It does not react. I already mentioned that they're very selfish because they already have full orbitals. They have all the electrons they need. They don't want to add or lose electrons. They're not going to be charged because they have full octets, full orbitals. They're very, very stable. So that's why we do this configuration, because we're not changing around noble gases. The electrons that do react are used after the noble gas. So to form bonds are the ones past this noble gas. That's also the valence electron. These are the electrons that we are usually interested in. Let's write a note. So we hide the core of unreactive electrons that follow the pattern. So you just, if I pick an element randomly, look and find the noble gas on the previous row, and we start from there. So it could be from helium all the way down to radon. If I was to like start with neon and put it in for, brackets like that, I'm assuming everything before neon is 1s2, 2s2, and 2p6. So anything after that, I start with 3s. But let's get some practice. Oh, sorry. We kind of already, I'm already pointing to that. This is, I guess, extra. Locate the element for which you are writing. Let's do sulfur. What is the noble gas before sulfur? Okay, so I'm going to do in bracket neon, and then that's all the way up to 2p. So the next thing would be 2, not be 3, starting with row 3, 3s2, and that would be 3p1, 2, 3, 4. So you start it like that. On the next slides, I'm going to show you how I was able to instantly know what was next. Let me play around a little bit more and ask you, I'm going to just highlight an element. I don't want you to tell me what noble gas we're going to use. I don't know what MO is for, but what is a noble gas? Krypton, okay. 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 Xenon. Testing you. Yes. So this goes here, this goes here. So it would be radon. Just testing you. I wouldn't challenge you that much, but good to know. All right. Rows are very important. So you want to be able to like know, okay, where is it at? And I also kind of hinted at before that your column in groups 1 and 2 are going to be S. So I'm going to highlight this real quick. Your S block. Oh. Are columns 1 and 2, or groups 1 and 2. Your P block. Or is that last block? It does combine some metalloids, non-metals, and metals, but it's the entire block. Do you have another like color? Okay. Your transition metals. That's gonna be your D block. And then your F block is the lanthanoids and actinoids. I know I'm a talented artist. I can't draw in the line. But yeah, so as we go across, we kind of go across this way. You always start lowest to highest, so go by row. So you start with the S's and then you move down. I do want to, let me fix one thing. Helium does belong over here. That's like one mistake that this kind of shows. Helium is an S. I think that's what they have right here. The rest of it is green, but helium is S. Okay. This just simplifies everything. Yeah, but helium over there. Now, here's how, if I was to use the noble gas configuration or try to do the electron configuration, I don't need that picture in front of me to do it. I don't need to have the low energy to high energy picture, everything ordered. And I just kind of have to read it like a book. I'm going left to right. So the first thing you want to do is you want to figure out, okay, where is my element I'm focusing on? And then you just read it from left to right. So I'm going to say my element I'm focusing on is somewhere in here. I'm going to, like it already has all of the rows labeled, but I'm just going to start in the top left. 1s. Okay. 2s. I can also assume the total number of electrons. If the element I'm focusing on is in the bless you, for P block, I'm assuming everything before then is full. So 1s would be 2, 2s 2. So here, check, check, check. Next would be 2p. How many electrons can I have in the P block? Okay, so 2p. Next would be 3s2. Check. Now we don't do 3d because it's on a different row. We have to finish the row. Check. Next would be 4s2, 3d10, and then you finally get to the 4p question mark. I know it's messy, but this is how you can kind of use the periodic table of elements to do an electron configuration without that picture in front of you. You just read it from left to right. So no matter what element we're focusing on, let's say it's down here, you have to just follow it. Now, if you get here, if I do 5D, the 4F comes before the 5D. That's when it gets a little tricky. It just takes a little bit extra practice. But I mean, the lower it is, the easier it is. Any questions on that? This is just going to require like us doing it over and over and over again, and which I will gladly do. So I'm not going to be always so nice. Are there questions?
So if you were given like whatever element and its charge, like if it's neutral, why can you not shorthand it even more? It's just like the last one is gonna fill in.
That's a great question. Typically, you shorthand it to the total valence electrons, like you want to have all of the valence, so it's the whole row. For it to be accurate, you have to include everything after noble gas. Like deep down, like if you were to say, okay, O2 minus is 2p6. I could definitely like understand where that's going from, but for it to be the most accurate, you want to be like, okay, helium and then 2s2, 2p6. Because it's all about the valence, and I'm going to explain that in a little bit. Like, what is the total number of outside electrons? The S is still very relevant. So like I said, I might give you the table on the right or the picture on the right. And it'll be very helpful because I might give you an element and say, okay, fill it in and tell me and write out the electron configuration. If you have the table on the right, your life is easy because all you gotta do is start from the bottom, which if a student hasn't done this yet, they might start from the top and go their way down. We don't want that to happen. Start from the bottom and work your way up. Easy peasy. But if I'm not so nice and I don't give you the thing on the right, you can still answer the question with the knowledge from the left. So it's like you're reading a book. You just go left to right, count the rows. So 1s2, 2s2, 2p6, and down and keep going. So as you're studying, keep this in front of you. The more you do it, the more it will stick with you. That's my biggest piece of advice. Don't try to cram this in the night before. Practice it, do the worksheets, do the homework, do whatever it can to be able to read this because you're probably may or may not be given this. If there is a question, I'll tell you now, this is the way to kind of cheat the system. If there is a question on the exam that gives you this, then you can always go back to it and kind of help yourself out. But you might not be given. Let's practice. Let's do two ways. Let's do the full configuration and then let's do the noble gas configuration. So magnesium, that's number 12, that's right here. What is the configuration? I'll have y'all write it out for me. Let's just assume it's neutral. What am I going to start with? 1s2, 2s2, 2p6, 3s2. Correct. That is the electron configuration. Now let's do it using the noble gas configuration. So the noble gas configuration is going to be this. So I can shorthand that by what is noble gas before magnesium? So I just gotta, in brackets, put neon, and then everything after, and that's the noble gas. All right, let's talk valence electrons. I'm not going to talk about the metals just yet, but the way that valence electrons go is you just pretty much count the electrons that's after the noble gas. So if I was to say how many valence electrons for magnesium, it's how many?
Just after the noble gas.
Yeah, just 2. That logic also applies for transition metals. It's when we get to the P block, it gets a little more complicated. But let's do cobalt. So what is the full? So this is cobalt is neutral. Walk me through the full electron configuration. What do I start with? Okay. Someone else? So we did 1s. We're done with 1s. What's next? 2s2. So we've done 2s. What's next? So cobalt somewhere in here. So it'll be 2p6. So we finished the 2 row. Right? Well, let's do the next row. What's next? How many? We're right now assuming they're full. So that's why I'm throwing in those numbers. So 3s2. 3p6. All right. What's next? 4s2. So we did 4s. And then, so start with scandium. 1, 2, 3, 4, 5, 6, 7. 3, 7. So this number should add up to be 27. So 2 plus 2 plus 6 plus 2 plus 6 plus 2, 7 should add up to be 27. What is a noble gas before cobalt? It's argon, and I have in brackets what argon would be. It would stop at the 3p6. So this is equal to argon 4s2 3p7. This follows the same logic of anything past the noble gas, that's how many valence. So how many valence electrons for cobalt? 9. 2 plus 7, yes. 9. Y'all, were y'all able to like see how I was able to go from the full electron to the noble gas? It gets a little bit different for valence electrons when you get past into the p block, but everything else is very straightforward. So tellurium, so let's start going from left to right. 1s 1, 2, 2, sorry, 1s2, then 2s2. Let me find where it's at. It's in the, I think it's in here, 5p. 2s2, 2p6. Okay, and then the next row, 3s2, 3p6. And then the next row, 4s2, 3b10, 4p6. All right, now we're in the right row. 5s2. I'm gonna make this smaller, sorry. Y'all keep going. All right, so tellurium, 1, 2, 3, 4. It'd be 5p4. Do y'all see how I'm able to get the number, the last electrons? Because if I filled in that full 4d orbital, that would be a 4d10. And then if I kept counting how many, because these should all add up to be the total number of electrons. But starting at the p block, starting at the boron, so each column 1, 2, 3, 4. So if I put brackets around there, this would be, yeah. I'm going to skip the valence electrons because it's different. It's not going to be the total. You would actually do the total without the D block if you did valence, but I'll talk about that in a little bit. Yeah. As you keep going further and further and further, it does get a little bit more bulk to it, but it's doable if you can kind of remember going left to right, left to right. Keep filling everything. If you want to double check your numbers, just make sure it adds up to the right number. Tellurium is number 52. So as you add them up, it should have 52 electrons total, if you want to check your numbers. Any questions on that? Okay. Let's talk about valence. So previously, if we are just talking about the S block, it's the valence, it's going to be the column. So column 1 and column 2 will be the valence electrons. So for column 1, hydrogen all the way down, it'll have 1 valence electron. So that's every number after the last one. For column 2, same concept. And that kind of keeps going all the way for transition metals. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if we ignore the p block, then whatever column the S and the D block are in, that's your valence electrons. Very helpful. When we talk about the P block, it's a little different. I kind of want to just ignore the D block. So, you would kind of like take out the 1 here and just do 3, 4, 5, 6, 7, 8. So we just ignore the D block, take out those 10. And then if I was to say, what is the valence electrons of oxygen? You go above it and just say it's 6. So this is a little confusing, but it's very doable the more you do. So how about I highlight some and see if we remember. So remember, if it is D block including, it's just going to be the column it's in. So S and D block, column it's in, that's the valence electron. If it's P block, just take out the D block. So literally, I took the columns and just took out the ones in front. So 3, 4, 5, 6, 7, 8. So I'm going to highlight some random ones. Just spit out what is the valence electron. Yeah. So find the column. That's going to be the valence electrons. Exactly. So it's kind of the same concept, but it's not 17. You take out the whole D block, you take out those 10, and it's now 7. And I'm not even going to do the lanthanides. No, it's not going to happen. Okay. Three. So it's not so bad. My advice is, since you're really comfortable with this now, try to like keep thinking about this while we have class, obviously on the weekends and in between. I'm not going to ask you to like really try to memorize, but just takes you getting comfortable with it. Just keep thinking about it using this method. And I wish I could make it a little bit less confusing, but kind of like let the columns tell you the valence. The electrons will always prove you right too, but this is a shorthand way of always knowing. Ground state versus excited state. Up until now, we've done everything in the ground state because that's the lowest energy. So you always start low to high. So if all of your electrons are in the ground state, you just do the same method we've done before. Same electron configuration before, but very rarely, if I was to add light or something to excite an electron, it's no longer in the excited state. So let me show you an example of what I mean. Let's do boron. Boron. Ground state. The electron configuration, let's say it would be 1s. If it's in ground state, you treat it the way that we've been doing. So boron is number 5. So 1, 2, 3, 4, 5. So you fill in the lowest energy and you work your way up. That is ground state. Excited state means that maybe one of your electrons is just no longer in the lowest energy state. Do you see the difference that I have from the left to the right? On the left, I'm filling in low to high. On the right, one of my electrons from the 2s orbital is now in the 2p orbital. So I did something to it. You're not gonna have to memorize where it goes or think. I'm just giving you an example of the electrons don't fit the narrative that we've been discussing. It's no longer going low to high. That's just the difference between ground and excited state. So it's any other arrangement from what we've discussed so far. I'm not gonna have y'all be tested on that. I'm just gonna emphasize that's the difference between what we've been doing and an excited state. My advice is for your exam, I'm going to give you a periodic table of elements that looks just like this. I'm not going to give it to you marked up, but what you can do to make your lives a little bit easier is to help yourself by marking it up. What Dr. Patterson and myself would recommend is writing out those column numbers on both sides. You can also like make a note that this is the S block. This is the D block. The P block. This is the F block. So like you can kind of make your lives a little bit easier on the exam by doing that. You can also like, you know, highlight these numbers, these column numbers. That could help you with valence if I was to ask you valence, and then maybe do 3, 4, 5, 6, 7, 8. That like these are good ways to like help you. But if you have a method that works best for you, like you don't have to do what I do. But this is how like I can help myself. Like how do I go from, you know, silver? Like okay, so start with 1. If we have 1s2, 2s2, 2p2, 3s2, 3p2, 4s2, 3d10, 4s6, 5s2, 4d, yes, 9. So like that's how you can kind of set yourself up on the exam to help you if you don't have it memorized. So I definitely recommend having these rows on both sides to like really double check your numbers. Any questions on that? Where do we go next? So I think we're going to move on to Lewis dot structures next. But atoms gain, lose, or share electrons. I think what I would definitely do, especially like on the worksheet, which will come back next class and we'll continue working on it, is what happens if I take away and gain those electrons. We've been doing the practice today also, but that's going to be a really good challenge. So I do recommend trying to do the worksheet. So what's happening there? What arrangements of atoms are stable? That's definitely going to be more in Gen Chem 1, is having the best stable atoms, and then what do these arrangements look like? That's where we're going next. As you go on in chemistry, we kind of take our fundamentals that we're learning in this class and in general chemistry, and we apply it to even further. So if you happen to need to take organic chemistry, the orbitals tell you a lot. So they extend the idea of orbitals, shapes with a high probability of finding electrons. I'll give you a hint. These orbitals also tell you about double and single bonds, and it moves even more past that. So this is a really important fundamentals class, even though we're not always thinking about this when we move further on, but we're setting you up for futures. Sometimes if you have more than 2 elements, can you do a electron diagram or things like that? So obviously you're not going to be tested on this, but this just shows why it's important, especially if you do happen to need to take upper level chemistry. All right. Any questions? Okay, so we have 6 more minutes. Let's work on the worksheet. And then next class, we'll come in and go over those answers. I'll give you some more time to work on the worksheet next class, but let's get a little head start for next class, for the next 6 minutes. If you're online, I'll get the worksheet up in front of you. The back page is going to be a lot of fun because the back page is just doing electron configurations. So if you feel good, I do recommend like maybe having some notes in front of you while you're still learning. But if you can do the back page with a blank periodic table of elements, you're ready for the exam. Yes, the 1s2, the 2s2. If you don't feel like answering all of these, you can always just start with just doing the full electron configuration and the noble gas.